Welcome back. In this lesson, we are going to put everything together. So we are going to implement the full algorithm of the decision tree, right? And as we said before, it's a recursive algorithm, right? Or it's an iterative algorithm. So what do we mean exactly by recursion? It means that the solution of the algorithm itself is the algorithm itself, right? So it can be confusing to understand what is recursion, but this is actually what is recursion is, right? Recursion, when we have a program and we want to get the output of this program, the output of the program is the output of the program itself, right? So in order to get the output of the program, we need to call the program again or to call the function again. So if we have a recursive function, then this means in order to get the output of this function, we need to call inside the function itself the same function, right? So we are going to see this in a moment. So in order not to have an infinite loop or an infinite recursion, we need to have a base case. So a base case is a stopping condition in recursion. And in our case, the stopping condition is for splitting, right? And it can be one of the following. If all the data points in the node have the same label, right? So if we have the left subtree or the right subtree, all data points have the same label, right? So the entropy is basically equal to 0, then we should stop. And if the current node is at the maximum level, so we can define a variable called the maximum depth or the maximum level. If we found that the current node is at this level, then we will stop, right? And we may assign the mode of the labels as the class label. Okay, so these are the two stopping conditions we are going to use. And in order to implement the full decision tree, we are going to use a class. So you might want to revise the object-oriented programming part we explained in a previous lab, right? In a previous section. We are going to use also a dictionary to store the tree information. So this dictionary will contain the class labels, feature, and value to split, and the reference to the right and left children. So if we look at one of the trees, right, or one of the nodes, you will see that we have, for example, a key called isLeaf. So this means this is a leaf node. If the value for this key is false, then this means it's not a leaf. And if it's true, then this means it's a leaf, right? And this is the split attribute for this current node and the split value for this current node. And we also need to store if it's categorical or numerical for future reference. And the most two important keys in our node is the left tree and the right tree. So the left tree will be an instance of the class itself. So the left tree will be a node by itself, and the right tree will be also a node by itself. Okay, we will understand all this in just a moment. So the final output or the final algorithm should work as follows. We start from a very basic decision node based on one split value and split attribute, and then we are going to go either in the left direction or in the right direction. So as you can see, this is actually a tree by itself, right? So we can perform recursion here. We can perform the iterations again here. The same algorithm can be performed right here. So we say that this is the node, the actual node or the starting node, and we want to split either left or right. And if this is the last node, then this means it's a leaf node. So we have here a leaf node, another leaf node here, another leaf node here, and then another leaf node here, and another one here. If you want to see this graph and if you want to know more about this graph, you can go to this link and see this tutorial on decision trees in order to understand better. But I can guarantee that using this videos only, you will understand everything there and much more. Now, let's implement our class. So here we are creating a class and we will call this class my decision tree. And if you remember from the object-oriented programming section, we said that we need an initialization function, right? So this will initialize the initial values, right? So this will set the initial values for all the parameters we have. So we have only one parameter called maximum depth, and of course we need the self in order to differentiate the objects from each other. So here we have self.tree, right, equal an empty decision tree, right? So here we are creating a tree, right, the tree itself, and this tree or this node is an empty dictionary, right? And here we are creating something called residual tree, and we will use this for prediction, okay? And we have also another parameter called the maximum depth, so we can stop the recursion, okay? So this is the initialization. This is what happens when we create an object of this class, right? Now we have the most important function is the fit function. So this is how we will fit the data. This should be very similar when we call it to the sklearn implementation, and we will see this in a future lesson. So what are the inputs for the fit function? First, the input for any function in the class is the self itself, right? And then we have x, y, and depth, right? So x corresponds to the data points, y corresponds to the labels, and the depth, of course, corresponds to the depth of the current node. And the output should be a dictionary that contains this node information, right? So something like this. Now, how we implement the fit function? First, we are going to get the unique values of y, right? So if the unique values are equal to 1, the length of them equal to 1, so this means that we meet the first stopping condition. All the data points in that node have the same label, so we will stop, right? And for the second condition, depth equal maximum depth. So if we met this condition or we met this condition, we will return the classification. So how we get the classification? We will use nb.unique. So nb.unique will return the unique labels, and if we return counts also, then we have the counts of the unique labels, right? And then we are going to the argmax, right? Argmax will return the index of the maximum, okay? So if we have two labels, the first label is 3 and the second label, the count of it is 10, then we are going to classify all of them as 1, right? So if we have, for example, here, let's say 1 and 0 and 1 and 1, this is, we reached the maximum depth. So in this case, the classification will be 1. So this is basically very similar to the voting we saw in the KNN, right? Now, this is the base cases, right? So as you can see, in this case, we return the classification for this node. Now, if we didn't reach one of these base cases yet, then we are going to call the functions we created, right? So we are going first to call find best feature. So this is step 1, right? To find the feature, the best feature, and the best split. And then we have the second step, which is find best split. This will return the best split and the information gain associated with it, right? And then we are going to call partition classes, right? And this should take x, y, best feature, and best split. And if you just hover over here, you will see that from the docstring we created, we can see a documentation for the function. So this is pretty neat, right? You might notice that we have an extra step here, or a redundant step here, which is step 2, because step 2 is actually called in step 1, right? So from step 1, we can find the best split, and we can actually find the best information gain. And even if we don't, it doesn't really matter because we are not utilizing the information gain in this code, right? It's actually used in the utility functions or in these functions. So we can just remove step 2, right? Remove the calling of step 2. But step 2, of course, is called inside find best feature. Now, after we find the best feature and find the best split, we call the partition classes with the best feature and the best split, and this should return the x left, x right, y left, and y right, right? Now, if the best split is actually a string, then we will have a question just like this, right? So this is the format of the question. So we will represent the subtree as a question and an answer, right? So as you can see, if it's a string, then we are going to say the question is the best feature equal, the best split or not, right? Else, so if it's a numerical, then we are going to have the question just like this. So we are going to say, is the best feature less than or equal the best split or not? Okay, so this is how we can create the nodes. And we will see in just a moment how this is structured. Okay, so the node, as you can see, is a dictionary, right? It's a dictionary. And the key for this dictionary is the question itself. And the answer, we still don't know the answer, right? Now, the answer for the first subtree, the right subtree, is actually the left and right subtrees of this subtree, right? So, for example, here we have a question and the answer can be either true or false, right? So this is the question, and the answers for this question is this decision node or this decision node. And for this one, the answers are this node and this node, right? So let's continue. Here we want to find the answers using recursion, right? So we will increase the depth by 1, right? Because here the depth is 0. Here the depth is 1, here the depth is 2, here the depth is 3, right? So we are going to increase the depth by 1. Now, the yes answer is the left subtree. So if you notice, we are calling the same function, right? So inside the fit function, we are calling the fit function again. But we are calling it right now with x left instead of x, and with y left instead of y, and with the current depth instead of the maximum depth. And for the no answer, we are going to have the right x and right y and also the depth. So this is the part where we perform recursion, right? So in order to get the solution, we need to call the same function we are inside, right? And when this function is called, it will be called again, and then it will be called again, and then we backtrack, right? So when we backtrack, when we reach one of the base cases, right? So this is how we can get the yes answer and the no answer. Now, if the yes answer is equal to the no answer, so this means that the node can be only yes answer. So basically, if we have this leaf node is equal to this leaf node, then it doesn't matter. We don't really need the two nodes, right? We can just get one of the nodes and that's it, right? But if it's not the case, and most probably it will not be the case, then we are going inside the dictionary, right? And for the question, we are going to append the yes answer. So we are going to append the questions to the answers, and the same for the no, right? And finally, we will say that our tree is actually the node, right? So the current node by the end should be the complete tree. So the recursion, so what the recursion will do is basically build this leaf node, right? So we will go into this direction, call the function again, and then go here. Then we reach a base case. So this leaf node is created, then this decision node is created, and then this leaf node is created, and then this decision node is updated, and then we go here, and then here, and so on, right? So this is how the recursion works. So by the end, the node is actually the complete tree, okay? So that's why we are saying self.tree equal node, and we should return from the fit function the node itself or the tree itself, right? So this is how we can perform the fitting, how we can build the tree. Now, how we can predict using this tree. Let's first understand it on the graph, right? So let's say here that this is the first question, this is the second question, the third question, and the fourth question, right? So we will first start by looking at the feature that corresponds to question number 1, right? And based on the split value for this specific example, right, or the query or the test point, we are going either in this direction or in this direction. And if we go to this direction, for example, then we are going either in this direction or in this direction, right? If we reach a leaf node, then we are going to get the predictions of the leaf node. That's it. It's very, very, very easy to understand and very, very simple and intuitive. So let's see how we can implement the predict function. So here we have the self, of course, and we have the record. So the record is basically a single data point that should be classified. This is the one we want to predict. And we have a flag equal to 1, and we will see what this flag is doing. This flag is only for knowing if this is the first time or not, right? Because if we are calling this function for the first time, then the residual tree, or the tree we want to use for prediction, is actually the complete tree, right? So first we want to use the complete tree, but if we reach this part, then this part is redundant, right? The new tree is actually this tree, right? So for the fitting, we build the tree from the ground up, but when we are using the predict function, we use the complete tree first, and then we tear this tree down, right? So this is how we use the fit and we use the predict. And we actually have a recursion in the predict function, as you are going to see, right? So here we have flag, if flag equal 1, then the residual tree is the complete tree. And then we try to fetch the question. How we can do so? We are going to go to the residual tree and then use the keys function in the dictionaries. And we discussed it before when we discussed the dictionaries and we learned about dictionaries. And this will be a list, right? So we want to get the first index of the list, right? This will correspond to the complete question. And as we can see, the question is actually in a form of a string, right? So if we use the split function in the strings, then this should return the feature, right? And equal or less than or equal, and the split value, right? So as you can see here, feature, comparison, and value. So if the comparison is equal, then this is a string. If it's less than or equal, then this is a numerical attribute, right? So if it's a string, then we are going to the record, right? The record is the point we want to classify. And then we will go to this feature and convert it to an integer, right? The feature should be a string, right? It will be a string, right? Because it's inside a string. So if it's 3 like this, we want to convert it to integer. So we will perform a typecasting. So we will have, instead of 3 between brackets, it will be 3 like this, right? So we want to go to index number 3 in the record, right? And if the value of this feature, right, is equal to the value, then the answer should be the left subtree, right? Because that's how we perform the string comparison, right? And if it's not equal, then we go to the right subtree. So how we can go to the left or the right subtree? We go to the residual tree, right? And we go to the question inside the residual tree, and then we go to 0. So 0 is the left subtree and 1 is the right subtree. Why? Because we did it like this. We said that we are going to append first the yes answer, and then we are going to append the no answer, right? Now, after that, if the comparison is less than or equal, then this means it's an integer. So instead of just having equal here, we will have less than or equal, right? It should be exactly the same. Now, what is the base case for this predict function? The base case, if we have an answer, right? So we stop when the answer is not a dictionary. So the answer is basically a value. If it's a dictionary, then this means that we are still getting subtrees and we still didn't really get deep enough. So we didn't reach the maximum depth, or we are still have some information left, right? So this is the base case. And if we didn't reach this base case, then we are going to perform recursion. How? First, we are going to say that the residual tree, right? The residual tree at the beginning was the actual tree, the complete tree we built in the fit function, right? But right now, the residual tree will be the answer. So the subtree, either the right subtree or the left subtree, right? So first time it will be for example, the left subtree, and then the second time it will be this right subtree, and then it will be this right subtree, and then finally we will reach an answer, right? So in this case, we will stop. Okay, so that's how we perform recursion. And then the recursion is here because we are calling self.predict, the same function we are inside, right? But now we are calling the flag. We are using the flag equal to 0 instead of equal to 1. So the first time we call the predict function, it will be 1. The flag will be 1, right? So the residual tree will be the complete tree. And then each time we perform recursion, the flag will be 0. So the residual tree will be the tree we built in the last iteration or in the last recursion. Okay, so this is the fit function, and this is the predict function. Now, in the next lesson, we will see how we can evaluate the decision tree. So how we can write a function to evaluate our decision tree, and then we will see what is the final tree. So this is basically the final tree we can get. It's not visualized yet, but this is how we structured it using a dictionary. Okay, so we will understand how we can evaluate our model and how we can see the final tree as a dictionary, right? So let's go to the next lesson.